Hello, everybody. Welcome to In the Code Garden, the Advent of Code Garden series. This is our second episode of this series, and I'm Renee Noble, the Regional Cloud Advocate for Microsoft Reactor for the Australia-New Zealand region, and I am joined here today by Jack Reichelt, our guest co-host for this series, who is absolutely obsessed, I'm going to say, with Advent of Code. He's also the CTO of Connected Code and the founder of Adventure Events, where he is a professional game master. So he loves to play Dungeons and Dragons and all kinds of things, but also on the Connected Code side, get out there and make really cool tech to help kids engage with learning technology and coding. So pleasure to have you back for episode 2, Jack.
Yeah, pleasure to be back. I really enjoyed doing episode 1.
Yay, excellent. So today we're going to be doing problems 6 to 8 of Advent of Code. So we did 1 through 5 speedily last episode, and then today we're going to talk about getting speedy or working well with data in this episode of Advent of Code. So let's see what we're going to do today. So first we're just going to warm up with problem 6. It's not too tricky. Then we're going to get into the weeds a bit more with problem 7, where we're dealing with classes and recursion for the first time in the problems this year so far. And then we're going to go on to problem 8, and we're going to talk about a little bit about dealing with two-dimensional maps, which come up fairly often in Advent of Code. So we've got a few tips and tricks for you there. Today, we're going to be using Visual Studio Code for all of our coding. We're coding in Python, so we've got the Python extension installed as well. And so if you're following along with Python, you can do that too. You can code Advent of Code in any language of your choice. But we're going to show you our tips and tricks in Python today. This time around, we have got the live share extension to participate with us. So I will also be showing off that so Jack and I can work on the same code together. So that's going to be exciting. We've got a couple of links for you today. We've got our Cloud Skills Challenge that we've set up. So if you want to get some more Python skills and practice some things that'll come in handy during Advent of Code, you can try out our Cloud Skills Challenge. It's got a few different Python things for you to learn in there. We've also got the Advent of Code link for getting to the problems. And we've got a leaderboard that you can join from the private leaderboards channel. We've also got all these links on... I'm not sure that a Cloud Skills Challenge is on there. I'll put the Cloud Skills Challenge on there later too. But we've got the links to Advent of Code and to the private leaderboard page on this repo, where we're also putting all the code we're writing during the stream. So you can jump on all of those. Maybe Sarah will drop those in the chat for us. But we're going to move on to coding today's problems.
Yeah.
Let's have a look at today's first problem. So, excellent. Okie dokie. So we're up to problem 6. Yeah. So we didn't actually put the solutions in for days 4 and 5 because we're running out of time at the end there. But we do have the code up for you on the site, so you can do yours yourself. First we're talking about day 6. So do you want to explain to us what day 6 is about, Jack?
Sure. So the problem for day 6 is the elves are heading into the jungle to try and make their way to the Starfruit Grove, and so they all distribute communication devices, but yours is faulty, and so we need to reprogram it to make it work correctly. And what it is, if we scroll down a bit, is that we're getting this data stream here. Here's an example one up the top here, which is just a whole bunch of random characters. And for part 1, what we have to do is try and find the first 4 characters where all 4 of the characters are different. And that is going to be the what this problem is calling the start of packet marker. And so really what we've got to do is just step through 4 characters at a time and see if all 4 of the characters are unique.
Absolutely, cool. So yes, we can see here that the start of packet marker isn't always at the start of the packet. It goes on to give us some examples. So we'll have a look down here for these ones. So the first start of packet marker, which is the first 4 unique characters, starts at character 5. So you got 1, 2, 3.
No, it ends at character 5.
Oh, ends at character 5. Right. Oh, there we go. Perfect. So we can see V, W, B, J. They're all unique. So we know that the packet starts from here. We are just looking for where it ends. So we can get that. Yeah, we've got the first marker after 6 characters. So 1, 2, 3, 4, 5, 6. So we take these 4, P, D, V, J, etc. So we're going to find the first 4 unique things. So yeah, I guess we will start that by getting our own puzzle input for this one. As you can see, they're a little bit longer than the examples. So we definitely want to get some programming happening here today. Let me just get my VS Code window so we can have them next to each other.
Yep. And I've already set up some blank files for the VS Code for us.
Oh, fabulous. This is why you're a CTO. You're always prepared with the technology. Should mention that Jack is my lovely partner. He's joining me from the other room in our house today. So I can recommend him highly as a technology professional.
Oh, okay.
And person. Look at the recommend partner. That's taken. Okay, so let's jump onto the files that Jack has set up. Okie dokie. So we're up to problem 6 here today. I'm going to drop our data into the data.txt file. Give that a save, and then also go and pick up one of the examples from here. Let's start with this one here. Okay. Okie dokie. So we've got our data ready to go. So let's go to our Py file. Jack has started us off with his classic reading the file, which we saw a lot of times in the last episode. You always got to get that data out in one way or another. For this one, I actually started with the example. I just picked up the example one and I just hard-coded it in. That's what I'm going to say was my secret. If I just said signal.
That's very fair.
Yeah, because like if you're just getting started and you just want to do, just want to get started with something before even bothering doing the data, that is one option that you can do. But yeah, let's go with the data example. Day6 example.txt. So I'll get rid of this one. So I've got that. And then I'm going to lost my code. Here it is. So this one, very chill problem. This one, I'm going to say, everything, if it's your first time and you've got to day 6, that's pretty fantastic. But this one should be a little bit of a little bit of a break from some of the ones that I'd say were harder earlier in the competition so far. So
yes, a bit of forewarning. It's a little breather before the next puzzle.
Absolutely. So I guess we want to start by just going through our data, Jack. Do you want to chuck in your for loop that you have available? I think your code is basically identical to mine. So sometimes you just end up with the exact same solutions to something.
Yeah, so let's not spoil everything just yet. But let's standardize the spaces. So what I have here is I have we're just looping through the data, and then we shouldn't ever hit the end of this range, but I just wanted to make sure. So I've capped how far it can go through to be the length of the data minus 4, because we need to be reading 4 characters, and so we don't want to get to the end of it and try and read characters that aren't there, because that would cause an error. And then I get us a chunk by getting the slice of the data from the current position to the current position plus 4. One important thing with this slice and with this range is that you actually need to be this does not include the last character. So if I had I'll do a little example here of like if I had 1, 2, 3, 4, 5 and I said get me all of the characters from 0 to 4, given that it's 0 indexed, we would actually get just 1, 2, 3, 4, and it does not include the 4th character there. I really should have used letters rather than numbers, but
that's okay. I've done one down here in the bottom for you.
better. That's much better.
You can't see because you're all obviously on the screen there you're typing that. But yeah, just done a little example here in the terminal down below. It's not inclusive of the last letter of the last number in the range. But yes, probably want to start at 0 with the 0th index. Also happen if you just do range 5. So yeah, this one here is just saying whatever the end number is. But yeah.
And then that's true for the slice as well. It works in the exact same way. And so even though we're saying get us from I to I plus 4, that's only going to get I plus 1, I plus 2, I plus 3. And so that will get us 4 characters. And so then let's, as a little test here, just print out the chunk. And I'll like that. And then I don't know if I can run this in the live share.
Not that everyone else will see, but yes, as you can see, I've done a little example of the slice doing the same thing. So we get the first 4.
I can see that down the bottom. I just can't run the code that I wrote.
Yes, I will run the code now that I've left that thing, and then we can see that we've got a problem because something doesn't exist. Example.
Open. Oh, because we haven't CD'd into the right thing.
Oh, of course. Yes, because I restarted everything to make sure it was all working. CD, where are we?
I think you're in. Yeah, there we go.
Okay. Cool. Okay, great. Now we can run it. Okay, cool. So it's given us 4 bits at a time.
Yeah. And if we have a look at the day 6 example, we can see that the first one that prints out is BVWB, and that's the first 4 characters of the example.
Yes. Where is the example text? Here it is. I'll just bring that across so we can have a look over here.
Yeah. So then I've got another little bit here, which I've added in, which is now we need to check if they're all unique. Now, you can do this by comparing each letter to each other letter and saying, if the first one is not equal to the second, third, and fourth, and then if the second one's not equal to the third and fourth, and if the third one's not equal to the fourth, then we're all good. But that takes a lot of conditions and is tedious to write. So we're coming back to one of my favorite data types here, and we're doing more sets. Because if you convert a string to a set, and then its length stays the same, you know that all of the characters are unique. Is because, as a little refresher from the last episode, every element in a set has to be unique. So to see, I think I can write down in this terminal down here. Nope, I cannot edit a read-only terminal. Oh, but I click a button that asks me if I can.
Make the terminal read write for everyone. I've done something.
Great.
A new feature I didn't know about.
Hey, cool. So if I do like
Oh yes, exciting.
Yeah, so I got Python 3 up here. So if I do like my stir equals hello, if I do then set my stir, I get E, O, H, and L, but there's only one L. You'll also notice that they're not in the same order. Sets don't guarantee any particular order. And that's okay. We don't really care about the order of the letters. We just care at the end of it, after we've converted our chunk into a set, does it still have 4 characters? Because if it does, then they're all different. And so that means that we found the start of packet marker. Yeah. And so then we can print that chunk out, say where we found it. So the reason we're doing I plus 4 here is because the example wanted the end character, not the start character. And then we say break because we found it. We don't need to keep going. So if we run this code now, and that I still can't do, so Renee will have to do that.
Good. Yes.
Cool. Then we found for this example VWBJ, and that's at 0.5, which is...
That's the example's correct answer.
Yeah, first marker after character 5.
Cool. Great. I'm just dropping in the chat. If you do want to learn more about sets, just as Jack mentioned, it's just great to upskill on them. for advent of code or just your general life purposes. I'm just dropping in the chat where I taught sets earlier this year that might be useful. So we've got a couple of Code Garden episodes on data structures. I'll drop a few more in during this show because there's some really great data structure stuff going on in the show. Cool.
Definitely. So I changed that over to reading from the data file now. So if we run that, we'll get our real answer.
Fabulous. Okay, 1042. So let's go and put that in the thing. Okay, we've got our first gold star of the episode. Nailed it.
Huzzah.
Okay,
Great.
on to part 2, which is really very similar to part 1. If you've followed so far, you'll be great. I did want to mention something about break, though. If you haven't used break, what that means is inside an if statement or wherever you want, you can use break. And what it does is it escapes out of the innermost loop that you're in. So yeah, if we say break, we're going to stop looping at that point. And that means we'll have, the latest I on hand because we've, stopped getting new I's and therefore we're on hand to print that out. But yeah, let's go on to part 2.
I mean, in this example, we actually print the I beforehand.
Oh, yes.
But it does mean that we don't keep printing out every other valid start of packet that could possibly be.
That's it. And yeah, we just get the 1 because we'll find 1 and then we'll stop looping, which is great because then we don't have to scroll up, which we don't want to do. We want to get on to part 2. So yeah, for part 2.
Part 2, we're now looking for a start of message marker, which follows the same rules. Every character has to be unique, except now it's 14 characters long rather than 4. So this actually means that it's really quite simple to do. Renee, do you want to explain this while I
you put in that. And basically, so far we've had code that looks for 4 unique characters. Now we need code that looks for 14 unique characters. So we can just use the exact same code, and wherever we had 4, we're just going to update it to 14. Or maybe you were clever and used a variable to say the character code length, and then you could just update that. But 4s become 14s, and I think we're ready to do the next one. So ready to run that. I can run that. That's right. That's my job.
Yep.
And the first start of message marker is at 2980. Cool. So that's it. So that second part, if you got through part 1, we're very confident that you can get part 2 as well.
Definitely.
Nice, easy one after 5 days. That was some of it getting pretty tricky by the end there. So that is, day 6 done. Tick. 2 stars.
Yeah.
Okay, let's go back to our problems and go on to day 7, which I think is the spiciest day so far.
Definitely.
Yeah, because, we're going to start getting into recursion. We're going to get some classes happening here because, let's talk about what we're doing. So this one, it looks like you're using Unix or something similar to traverse through the files on your computer. What are we looking for here? So basically, in this question, we want to find out things about the size of directories on this faulty device that you've been given, because we do need to install some additional software to make it work as well as everybody else's. They've given us the faulty one because they know how technically savvy we are. So that's a compliment, but also now we have to deal with all of this. These, if you've done any Unix things just in your terminal, just get a terminal up. Well, I guess we have the ones that we've been using in the bottom. It's just exactly what we've been doing down here to navigate to where we are in our folders, etc. So you can say CD, applications, ls, all those kinds of things, and it will right here. It's not giving us the size of the different files, but in this example, it's got the size printing out before the file sizes. So we're going to be doing
printing out if it's a directory.
Exactly, that's it. So we've got some directories. So when we do CD, we're changing directory. When we do ls, we are listing everything in the current directory, which could be more directories, dir A, for instance, or it could be a file that has a size and then a file name, some of which have extensions, but not necessarily. And then when we do cd, we might do cd ... to go back up to the parent directory, or sometimes we can do cd/ to go to the home, the starting directory. So that's what we've got going on. So what is our first objective, Jack, here?
So the thing that what we're trying to do first is find, we want to find the size of all of the directories and find the small directories. So in this case, they define a small directory as with a size of less than 100,000. But one important thing about each directory or folder is that its size includes the size of all of the directories below it. And so if you're familiar with recursion, you'll be instantly going there, okay, that sounds like a recursive problem. And it is. So in sort of non-computer speak, the size of a folder is the size of all of the files in the folder plus the size of all of the folders within that folder as well. And so then for each of those folders, you get the size of all their files and the size of the folders within them.
Yeah.
And we can see here.
Yeah, we can look at this tree. Look, we can understand any file system as a tree, really. So we've got our top level folder, then that has some folders inside of it. So A then has more folders and some files in it. So we have to look all the way down to the bottom of the tree and really add up everything that comes underneath A for the A folder, and repeat for things like the D folder, which it doesn't actually have any directories in it, but we add all these items up. And then finally, we do add up everything to get the size of the / the home directory. So it's all, you got to make that tree and really go through the tree and look at all the children in the tree to add it all up for whatever folder you are looking at.
Yeah. So now that we're moving into the more complex stage of the advent of code problems, I think a really useful thing to do is start thinking about classes and objects. So if you're fairly new to programming, you might have heard the term class, or you might have heard object-oriented programming, or various things like that. And so what I've got, I've started up on the day7 .py file.
Yep.
And I've also pasted the example.
You already got the example.
Yes, because the example is the same for everybody.
It makes a lot of sense.
Yes. And what I've got here is just the very beginnings of a class. Now I've just called this folder, and we're going to need, a folder is going to need to have some information. So it's probably useful if the folder has its own name. As we saw in the example, they're named things like / or A or A, B, C, D, various other things like that. So what we do is self.name, and then I'm going to add a name up here. We say equals name. Now, a bit of introduction to classes in Python. It's slightly different in other languages, but the concept is still there, just different terminology. We have this self parameter for our init function, and we have this self.name here, which is we're setting to name. So what this means is class is sort of like defining a shape. It's saying, okay, we're going to have, one class of thing, and let's say it's my car. So I'm going to have a class that is car. Not all cars are the same. I have, this type of car, you have that type of car. My car's white, your car's blue, all that sort of stuff. And so, but at the end of the day, they're both still cars. Well, that's kind of what we're doing here. We're saying that there are things called folders, and they all have similar properties. That's what this self.name thing is a property. But it can be different for different instances of that class or different objects. And so this self, whenever we see this self dot or self in the parameters of a method on the class, that's saying this function is operating on a specific instance of that class. It's not doing a broad thing for all members of that class. Like, to run with our example, if we banned cars, we would go car.ban. But if we banned my car, we would go like Jack's car dot ban. And in that case, Jack's car would be the self. It's a bit tricky. It takes a bit to get your head around. As we use it a little more, I'll come back to this later in the stream and point it out when we've got a more concrete example. But for now, we can just remember that self.name means the name of this specific instance is going to be set to whatever was passed in here.
Maybe A for the file, or not the file name here, but later we'll get to that. Yes.
Yeah. So we're going to need a name, and we're going to need a couple of other things that can start empty. So first we're going to need a list of subfolders. No, I want all lowercase. And this is just an empty dictionary at this point. And we can map the name of the subfolder to the actual instance of that class later. But we're also going to need as well self.files. And that's going to be a map of the name of a file to the size of that file. And so this is, for now, we'll edit this later, but this is for now the start of our class. So we could now do something like example equals folder test. And that would create an instance of the folder class. So this is an object where its name is test, and we've stored it in this variable. And that's how we use a class. Then once we had other things, other methods, we can do example dot, to run with my previous one, example dot ban. But that's kind of the start of our class, but we're not really doing anything with either of these. So I'm going to quickly paste in two methods from
just interject quickly?
Yeah, sure.
This is one way to set it up. There's a lot of ways to set up your class. So I used a class. I didn't call mine folder, I called mine directory, but in the same vein of things, gone, making this class first. And then I've actually gone and added contents all together. So you don't necessarily feel like, oh, I don't want to use any dictionaries. Are you going to be, just so I know, are you going to be putting objects into these dictionaries, Jack, or just names?
Just names.
Okay, cool. Yeah, so we'll go a couple of different ways, but I'm going to put in some actual objects. So I'm going to put more folders inside my list later, but Jack's going to be putting names into his list. I put folders, and I'll put another class that I've made called files. So you've got different options and approaches that you can take there, but this is the general structure of what the class might look like. And you can think about how you want to store data to create this tree structure in a whole bunch of different ways. So I'm going to comment that out, and we'll keep going with Jack's version.
Yeah, so I'll paste in two methods here that come from mine. And these are for adding a subfolder and adding a file. And as you might have seen in Renee's, Renee also has a parent parameter. And what I've done is I've said in mine that parent has a default value of none. And then we just do self.parent equals parent. Now, the reason I've said it's got a default value of none is if we look at the example, we actually start at this directory whose name is just slash, and it doesn't have any parent above it. It is what is called the root directory. It doesn't have a parent, and so it doesn't make sense to define what its parent is. Like, I guess you could work around it by defining itself as its own parent, but that's a bit tricky, and it's a bit messy. So I just like to leave parent as none, and that also means that I don't have to supply it if I don't want to. To quickly zoom through these functions, though, conscious of time, we have an add subfolder function that creates a new folder whose parent is self. So this is saying, now we're getting a bit tricky because we've got multiple selves going on, and that this new folder will have its own self in here secretly. But what this is saying is that the parent of the new folder is whatever folder we called it on. So if I had that example folder again, and I did example.add subfolder, blah, then blah's parent will be example. And this is how we start linking them together in that tree structure, so that we can then say, okay, well, go back to my parent, or things like that, so that we can navigate around. Then I add it into the subfolders dictionary. So the key there is just the name, and then we link to the object, and then I return the object. And we'll get to why I return it later, but this is a neat little trick that can save quite a lot of time on this problem. For adding a file, that's a lot quicker because I didn't have a file object or anything. The files don't have anything underneath them. Literally all we have for them is a file name and a file size. So I just put them in this dictionary that maps the name to the size. And that's all that we have there.
Interestingly, I've gone different route. I've made a different object for the file. So I've said leaf file because they're the leaves of our tree. So we get to them. That means there's nothing to further go on to, as Jack was saying. And I've made them their own class where they have a name and a size. So 2 different options you can follow there.
Yeah, and to do that, you just be like new file equals leaf file of f name f size, and then we could literally just have this be there like that, and that would all work out.
It works together.
But since we're copying in mine, I'll just leave it with how that was.
Yeah.
There we go. Cool. So then the last thing we need to do is work out what the folder size is. Now, here's where we start to get a bit tricky. So I'll explain this kind of line by line because I've done some complicated stuff, particularly on this line here. So we'll come back to that. But the file sizes is fairly easy. We've got this handy sum function, and we're just saying for all of the files of myself, or the files dictionary, get the values, because we don't actually care where the sizes come from or how many files it is or anything. All we care about is get the values of our files dictionary, which is just going to be the sizes, and we add them up, and that's the total file sizes in the folder. And that's nice and quick. Folder sizes, we're still doing this sum here. At the end of the day, we're still getting the same thing. We just have we have a list comprehension in here. Now, as we discussed last time, I love a list comprehension, but let's break it down. So we're starting with the values of all the subfolders. Again, this is what we're doing here. So this is the actual folder objects. And so essentially we've got a list of all the folder objects that are the subfolders to this one. And then for each of those, we're going to call the folder size function again, which is this one here. And so this is our recursion. So what that does is it steps down through the tree and calls the folder size. It steps down, and for all those folders, it calls the folder size. And then let's say that's as deep as it goes and none of them have any folders beneath them. Then it will just return the file sizes, and this will be 0. And so then it can step up. So this is where the recursion occurs in my code here. So we get all our folder sizes out, and now, having passed this whole list comprehension here, we have a list of sizes of all our subfolders. And so then we sum that up, and that gets us our folder sizes. And then we...
Just for anyone who's not super familiar, like it is hard to read a list comprehension if you're not familiar with them. So I've just written this again as a for loop, just so, yeah, you can see it's just going through. We could just start a counter saying we don't have any folders yet, and just going through each of the subfolders and then getting the size of that item and then adding it together. That's all we're doing there.
Yep, that is the exact same programmatically as this. It's just what you find easiest to read and write. And then we add those 2 numbers together, and then we return that. And then I had one handy little function. It's this was just for my convenience. I didn't want to have to remember what the size of small was. And so I defined an isSmall function that just gets its own folder size and returns if it's less than 100,000, which is what the problem said is small. So now we've done quite a lot of code, but we haven't yet actually started solving our problem.
Yeah.
All
we have
we've
the
done
concept of a solution, but we haven't actually read the data, looked at it in any way.
Yeah, all we've done is said, hey, this is what a folder is. We don't even know what's building the folders. You might have noticed that we haven't, well, I've got this data up here where we read from the example, but we're literally never using this yet. It's all theoretical, this class. But what we're going to do is I'm going to go down here below Renee's classes, and I'm going to kick us off with how I got started on this. So first I created a new folder that was the slash folder, and we can see, yeah, and we call that the root folder. That's just part of the nomenclature of tree structures in computer science, but really it just means like this is the one without a parent. This is where the whole thing starts. And so we create a folder, and then I've got this working directory that I set to root, and then I have a list of all folders that I set to root, or that just has root in it at the moment. This one here, you might be wondering what we're doing with that, and I'll come back to that in a second as we start to go through all the data. But the way, do you have anything to add about those bits, or shall I kick us off?
I think keep going, yeah.
Cool. So, going sort of blow by blow, we're going to loop through all of the data except the first one. So if we look in the example file, we can see that it starts with change directory into slash. We kind of already did that. When I said working dir equals root, that's basically saying, yeah, we've now changed into the root directory. The working dir keeps track of which directory we're working in at the moment. And CD stands for change directory, which would change our working directory. So I've actually kind of just manually hard-coded that CD slash at the start. And I knew I could do that because I had a quick look at the day 7 data, which we haven't pasted in here yet. And that started with a CD slash as well. So I just ran from there. It just saved a little bit of time and thinking and prevented me from having to code an edge case. So then what I wanted to do is, well, let's have a look at the day 7 example text for a second. Let's have a quick look and see if we can identify some things. So there's a couple of different formats of messages here. You'll notice that some of them start with this $sign at the beginning. If you're unfamiliar with Unix systems, or rather unfamiliar with using the terminal, the $sign just means this is a command that the user input. And when the $sign isn't there, it means this is the output of the previous command. And that output can be multiple lines. For example, line 2, we have $ls, which is short for list. And then it lists all of the files that are in the current working directory.
Yeah.
And so here we get 4 different files. Now, that means that we need to start parsing all of the lines in this example, and then later in our actual data one, which is a lot bigger. If we go and get the data at some point, we can show that.
Yeah, let's go grab that. Yes, I think like in looking at the data, what I thought, because at first, like I know Jack loves these kinds of problems where they're all like about implementing some sort of computer operating system or like a programming language. That's like his forte. But I don't think I've done many of those in the past myself, because I often turn up late in the competition when I'm like, oh boy, these take too long. Wait, we've already got a file for this. So yes, then I kind of
file just doesn't have content.
Too much. I'm gonna leave that and maybe come back to it later, and then obviously get busy with my many jobs and many things to do. and then don't end up doing it. But in this one, it's like, it's not actually too complex, but I think like if you start looking at it, you're like, oh boy, I have to do something with every line of this stuff, and I have to like, what do I do when I do ls? And I have to do something with the CDs, and then there's all these different kinds of data going on. But what I realized actually, let's go back to the example, is some of them, like if there's something that doesn't have a $sign, you know that it's some sort of contents. And if you have something that does have a $sign and a CD, it kind of tells you where the working directory is going to be. But I actually didn't care about the ls lines at all. Did you care about the ls lines, Jack?
Nope. In fact, I still have a spot in my code because I wanted to keep track of them in case it was relevant in part 2. But if we go back to the code, what we see here is I have, if the line starts with a $sign, then it is a command. Then I have some code to process if it's a $CD, which we'll get back to in a second. But I've got this, if it starts with $ls, then we pass and we do nothing here because nothing is there. It's the command is done. Yeah, that's basically it, right? Like we don't need to do anything with ls from our data here. So if we have CD, however, we have to split it up to get the various chunks, and then we get the destination out, which is part 2. So I'm splitting it on the space. And so if we look at the example, then that's, where's the CD? Here we go, $CDA. That has 2 spaces in it. And so by splitting on the space and then getting chunk 2, remembering it starts at 0, then that gets us A for that example. Then I'll talk about that special case in a second. But then we change the working directory to the subfolder of our working directory that has the same name. So this is why I made it be a dictionary mapping of names to the objects. That meant that we could just change the working directory with this one line down here on line 55. But there is a special name in Unix systems of ... And ... basically means go to my parent. And that's, I mean, that is explained in the input text, I believe. Yes, CD ... means move out one level. Yeah. And so this is why we have to keep track of the parent of things, and it just makes all this moving around nice and easy. And we can keep track of what the working directory is and move around relative to that. So that's handled moving around, but now we need to handle all the other cases of when there's an input, or when there's an output from the ls. For whatever reason, when I'm copying these in, it's really messing up all of the indentation and everything. So I've just got to fix that whenever I copy in. But if it's not a command, then it's a file, I guess, or directory. But a secret Unix thing is directories are files. Cool. So if the line starts with dir, we know it's a directory. And that means that we've got to add a new subfolder to our working directory. So we say create a new subfolder, and we pass in the name of that subfolder using the same kind of trick of splitting the line and getting the appropriate chunk. Now, if you remember, back at this add subfolder function, after we create it, we return a new subfolder as well. The reason for that is because I wanted to store it in a variable here so that then I could append it to my list of all folders. This will become very useful because, especially in part 2, but it was useful in part 1 because we needed to find all of the folders that are small. And that includes, well, and this just means that we can loop through this list of folders rather than traversing the whole tree and stepping down and stepping back up and having to deal with all of that fairly complicated programmatic stuff. Otherwise, it's a file, it's got a size and a name when we split it, and then we add the file using the function, using the method that we wrote before. So all of this code here parses now our input. So let's look again at what we actually want to get at. We want to get the sum of all of the sizes of all of the small directories. And so it's time for my favorite thing, which I'm going to have to talk through a bit because it's a big old complicated
I'll
list
start
comprehension.
writing this one as a for loop as well.
Yeah, that sounds great. Okay, so you might be asking, like, why am I writing these list comprehensions if they're so confusing to read? The answer to that is that they are, like many things, a skill. Once you get your head around list comprehensions and get a bit more used to how they work, they're actually really easy to read and they are quicker to write. And if you are aware of the infamous off by one errors that programmers often hit, list comprehensions, it's not impossible to get them, but it is a little easier to avoid off by one errors where you add all of the small folders except the last small folder or except the first small folder or things like that. List comprehension prevents that. So let's have a look at just the list comprehension here. So we're going to end up with a list that gets the folder size for each folder in all folders. So that's our X there. But it will actually only get that if X dot is small and there is an implicit is true there. We don't have to specifically say that. And so what this says is this will get us an array of all of the sizes of all of the folders that are small. And then we can sum them up. And then we print that all together. So Renee's done the same thing here where we keep our total size and we loop through all the folders. And if it is small, we add its size to the total and then we print that. So this is doing, again, all this code here is identical to all this code here. It's just a matter of what you prefer reading and writing. But now, if we run this, and yes, it's still set up to be on the example.
Okay.
But if Renee gives that a run, we shall see all small folders is 95437. And you can see we both get the same answer there because, as we said, both of these things are the same.
I'll get rid of number 2 now, but that's how you can do it if you're not up for the big list comprehension yet.
Yeah. And if we have a look at the problem on the Advent of Code site, we can see that 95,437 is the correct answer for the example.
Hooray.
So if we change that to be reading from the data, which I've now just done, and we run it again, we can see we have 1,348,005 is the size of all our small folders. So now Renee can go put that in.
Excellent. We've done it. Excellent.
We've done it.
Cool. Okay, before we move on to part 2, I'll just make a couple of comments. Like, mine is largely the same as Jack, but as I said, I've got a few different structures set up, but I think there are some core principles that are the same, but we've got them in different ways because you've got some, where is your all folders thing? You've got your all folder that is a list, whereas I've got my mapping of names to folders as a dictionary here outside of the class, but you kind of got yours inside of the class. But so it's really up to you where you want to put that mapping, but being able to get around to different folders easily by having them accessible somewhere is important, and then also making sure you can get to not randomly, but choose one to move to set the working directory by the name to get that, which I believe is what you do in here. Can you explain that part a little bit more again? Actually, Jack, it was a little bit confusing because we don't have the class on the screen at the same time.
No worries. One thing that I do want to say first, though, is that with the all folders, having it be a dictionary, you've got to be careful with that, because that means that each folder has to have a unique name.
Yes.
And so potentially, when using the real data, that isn't actually true.
Yes, because you could have a folder A inside of a different folder somewhere else and have it, in two different places or two different files with the same name, etc.
Yeah, and more to the point, I think that that's the kind of thing that the developer of Advent of Code often makes sure to include as an edge case. I am pretty sure that for this puzzle that does happen, and so if you do store.
I did have to add a path to mine, so mine might have been like directory, A, B, C, and then file, hello.txt or something. So I had to put them all together so I knew that it was, specifically the one I was looking for. So yeah, it does matter when you're setting it out where you're going to, what format you're going to put it, because you do need unique keys. But yeah, you do have options. It's not you have to do one way or the other, but you will need some way to navigate around.
Yep. So we wanted more detail on lines sort of 50, 52 to 55.
Yes.
Okay, cool. So for line 52 and 53, we're checking if the destination is ... That's the special secret shorthand for go to the parent of the current directory, or go up one level, or however you want to think about that.
And that's easy because we've already stored on the class the parent, as we saw here. We can just say directly, go to my parent. And that's
exactly.
Still.
And so on our variable working dir, we can just set the working dir to be the current working dir dot parent. Similarly, it works in the opposite direction with the subfolders. So we say working dir equals the working dir dot subfolders, and then we use square brackets and supply the destination. So the destination here is going to be the name. If we have a look at line 7 of the example file.
Line 7, yeah.
Of the example file.
Sorry.
Yep. So you can see here we have $CDA, and that says change us into the A directory.
I think I've figured out what might be a little confusing, because I was trying to follow it as you said it. But we do need to, we're dealing with the moving to directories here, but we have the creating the directories down in here. So we're talking about moving to directories that we kind of had an address that we were making already. So the first time you see a directory is going to be when it gets listed as one of the things when we're going through the lines, and it either starts with dir or it's a file. So we'll notice it then, but we won't move into the directory until we've already seen it before. So that way we can say, we already know who the subfolders are, we can go into it now.
Yeah, we could do something like this, which would be just a little check making sure that the destination is a valid destination in the subfolders. This is one of those cases where it comes down to sort of familiarity with Advent of Code. I think if I were writing a real computer system, that is absolutely correct, and what I've done here is bad and wrong. But I know that this is a puzzle, and I expected that we weren't going to have invalid commands. I expected that because in the description of the problem, there was no mention of invalid commands. All the commands in the example were valid. And so I made the assumption that anytime we got a CD into a subfolder, that subfolder existed, and following along with the layout of the list of the example, we had seen it before. And so I create the folders as we encounter them in the listing rather than as we try to move into them.
Yeah, and that's kind of different to my approach, where I believe I only created the folder when I moved into it. So once again, lots of different approaches to solving the problem. But with that, shall we quickly talk about part 2 before we move on? So,
yes, and
short on
give our
time.
last few tips. So part 2
What was it? Let's go look at the thing.
Yeah, so part 2 is about finding out what folder to delete. So it shows that we have a total space on the file system of 7 million or 70 million. I can't count the number of zeros. And you need at least 3 or 30.
30, 70 and 30.
Yeah, 70 and 30. Cool. So you need to find which directory you can delete to free up that much space. So let's get started with some of the logic for that.
So
I put in.
Know the total. We know we need it in some amount to be free. So far, we've only added up the small folders. So that's something I forgot. So I was like, oh, too easy. I already know the size of the stuff on here, but that was incorrect. So we're going to need to add up all of the stuff that we've used so far, so we can work out how much new space we need to make from that used space.
Yeah. So one handy thing about folder size, including all of the folders and all the files below, is that means that the folder size of the root is the same as like everything that is taken up. So we can find out how much free space we currently have by doing the total size minus the folder size of the root. And then we can work out how much space we need to clear by getting the needed free space and subtracting the current free space. And that gets us our difference there. Then we want to loop through all of the folders from smallest to biggest and find the smallest one that has a size bigger than this needed clearance. So what I did first was I sorted all my folders. So sorted
talk
creates
about this part.
Yeah. So sorted creates a new list that has sorted all of the elements in that list. So you provide the original one, in this case, all folders. And then I've got this key here. So there's nothing in just folder, the class folder, that says what one folder is better than the other. Like how are we sorting them? Are we sorting them alphabetically? Are we sorting them by, length of title? Are we sorting them by who was created first? Although we're not tracking that, but you could do all sorts of things. And so this key lets us provide a special little function, and we'll explain the lambda in a second, that lets us specify how we're going to sort them. So
shall we do a little example of a lambda in here for just like maybe some tuples? Often you might have a dictionary or something, and you have like two things you need to sort by. I did mention this for problem 5, but we didn't have much time to talk about it last time. But let's make a list of things. I'm just going to call my list A, and it's just going to have, let's say, it's going to have 2 items. One's going to be, one's going to be a string. One's going to be a number. So just put them in this order. So we'll need to change the order because we're going to sort this alphabetically, is what I'm saying we're going to do. And then let's say this can be 2. This can be A. Okay, so we're going to want this to be alphabetically. We don't actually want to sort by the numbers, for instance, but we want to, let's make that be fixed. Okay, put this wrong way around. Okay, so we've got this, and we want to sort that.
Yeah, let's show the normal sorted, yes.
So it would sort by the first part of the tuple. So this one does have an inherent order for this tuple, but as we're talking about, as Jack said, the class we've created doesn't have anything, so it has no idea how to sort it. But sometimes you just want to override it or set the way that you sort things on there. So for this one, we could say sorted key equals lambda. And lambda is like a function that you define just in this one line, and then it goes away. So you can't use it anymore. So it's good for a function that you just need for a moment in time. So we say lambda x because this has one bit of data that's going in. which is each item in the thing that we're sorting. And then we say we want to sort by not the 0th item, but the first item in the list, in the tuple for each of the positions. So we want to say we want to sort by X1. Yeah. So then we can run that, and then it will sort by A, S, T instead of 1, 2, 3. Yeah. Anything else you want to add on lambdas, Jack?
Yeah. So what I've done here is back up in the file, I've made just a little tiny function that I've called example lambda. So the important thing to remember is that a lambda is just a function. And so when we say lambda here, we're secretly saying do def, but a little differently. And then this x here is this x. And then the colon is this colon here. And then this bit here, it's got to be a single line essentially, but it just returns whatever we've put there. So this function here is the same as this lambda here. To the point where we could actually uncomment this and replace this lambda here with example lambda. And that's actually valid code, and that would work and do the exact same thing. But the lambdas are useful for having that sort of containing the problem to one spot. We don't need this function anywhere else. And so by putting it in here, it keeps everything that's related together.
Makes it your code nice and clean.
Yeah. So
cool.
Now we've got a list of folders that's sorted by size, and so you can just loop through them. And we check if the folder size is greater than the needed clearance or equal to. And if it is, then we print that the folder to delete and its size is the name of the folder and the folder size. And then we break because we found the smallest one. We don't need to print the extras. So part 2 here is definitely the smaller part, but it has a few tricky bits with mostly just this sorted and the lambda. But we did a lot of the loading.
If you didn't put anything in here, the code just simply won't run. Like when we ran this thing for these tuples here, it does run. It's just not the order we want. But this one will just not. It will just throw an error outright.
Yeah. Do you wanna run that then?
Let's get out of the. Yeah. You'll see.
Yeah, less than is not supported between instances of folder and folder. You can make that be supported. You can define how less than works on folders. So rather than a lambda here, we could have gone up to the folder and added a very specially named function to do stuff like that. But it's just easier to do this. So now if we run it with the lambda back in, we can see that the smallest folder is WJV, and that's what we've got to delete there. That's off the data one. We forgot to do it off the example, but let's do a quick run on.
They'll believe us it works on the example because it works on this one. Excellent. Okay, yeah. So yeah, that is how we went about, Jack's way, in which is similar to mine conceptually, but not exactly an implementation of getting through problem number 7. So shall we do a quick run through of what our advice is for question number 8?
Because we got one big tip.
Popular thing that happens a lot in Advent of Code, which is some sort of 2-dimensional map, essentially. And this one here is about you're talking about building a tree house, and luckily the elves have previously planted a field of trees in a perfect grid. And the rules for a tree house for part 1 is that the tree, you don't want your tree house to be seen from the outside anywhere. So we need to find somewhere in the grid that has coverage from every angle, from every direction, north, south, east, and west. So if we look at, let's say, this one here, so it's 3 high. So if we looked from the west direction, the left side, you couldn't see it because there's a tall tree that has a height of 6. These numbers are all the height of the tree. If we looked from the north direction, we couldn't see it because there's a tree with a height of 5. That would block it in that direction. And then same from the bottom, we have a 5 before we get to the 3 here. But we're looking from this direction in the east, we see a height of 2. Oh, we have one that's the same height. So actually, this was a poor choice. But yeah, we wouldn't be able to see this tree because there is a 3 that blocks the height of the tree. But some places on this map don't have coverage.
Choose the 5 just below that.
The 5 below it.
Yeah.
Perfect.
Yeah, that one can be seen to the left and to the south.
Yeah, so we've only got trees shorter in these directions. So we need to find a tree that, all the trees, I believe, that we won't be able to see. And then we need to add them up or something. What's our final output?
The first... Yeah, so the output of the first one is how many trees are visible from outside the grid. And so if you look at the puzzle input, we've actually got a huge number of trees. If you look, well, that's the example input, but in the puzzle input,
many trees.
Huge.
Don't do this by hand.
So many.
So we know we're going to be able to see all the ones on the edges, firstly, and then many others, especially if they're tall and they're near the edge or there's no other tall trees in their axes. So let's get this one. Shall we get started on our problem?
Well, we're already about 10 minutes over time, so I think we should just tell our big tip rather than actually code it.
Yeah, let's just paste in all the code, I reckon.
Okay, cool.
Just so we can point at things. Yes.
Yep. I'll pull that up in just a sec.
Cool. Okay, I'll make a file for the text, for the code
cool.
for the data.
Okay. So, once you've done that, I can point to the things. Yes, we have a comment from Sarah saying that she thinks she needs to refactor her day 7 and that she made things a bit overcomplicated. I think that that's extremely natural. I think that it's very easy to look at that kind of problem where you've got trees or other data structures, and then there's recursion, and then there's parsing, and there's quite a lot of elements to day 7 as a puzzle. And if we go to the stats page of Advent of Code, we can see on the website, we can see that there's actually quite a drop off of participants on day 7.
Okay.
So if you click stats,
here we go. Sorry for any noise in the background. There is a cat who does not like being locked in the office with us during the stream.
Yeah, so there was actually quite a lot of drop off between day 6 and day 7 because it was a big step up and it is a complicated problem with a lot of moving parts.
Absolutely.
So I've pasted in code for day 8, and I'm going to point out the magic line.
On Sarah's note, though, I would just also say, like, my code looks a little bit more chaotic than Jack's because I did do things like, because I had my file leaf data type and I had my directory data type. I did do things a little bit differently in terms of things. So I did do like testing for the type and stuff at points to be like, okay, is it a directory or is it a file? Because Jack went and separated his into 2 different sections, which maybe made it a little bit cleaner later, but it all works out in the end. Yeah, let's go on to, I've lost my screen. There we go.
There we go. So what I really want to focus on is these first few lines here, up to line 12, really from about 8 to 12.
That's it. Beautiful section.
In Advent of Code, there are often these infinite grids, or rather, sometimes finite, sometimes infinite, but there are often grids. And on a small size, like the example, having just a 2D array of the trees isn't going to be a big problem because there's only so many things. It can't, it's manageable and it's not going to be super inefficient. But as soon as it says infinite grid on any problem, I would really recommend you don't make an array. What I would recommend is you make a dictionary or a hash map or whatever your language refers to them as. And we'll get to what Renee's adding in a second. But this dictionary means that instead of having the whole 2D array, you can define you can have the elements so that it looks like this, where we have, say, at coordinate 0, 0, it maps to 5. And at coordinate 0, 1, that maps to 2, and so on. And this means that one advantage is that a dictionary has a constant time lookup. As you progress through advent of code, you're going to have to start caring more about your efficiency, as part 2 is going to throw some curveballs at you where your program that was a bit inefficient but got things done on the small size part 1, it's going to get a little tweak to it where now you have to do it a million times, and what took 1 second is now going to take a million seconds, and that is quick maths tells me that that is 277 hours, which is 11 days. That's bad. And so having this sort of layout means that you can actually only care about the data points where it's relevant. For instance, if there is no tree in 0, 2, you can just move straight on to 0, 3 and put a tree there. And you just don't have to have 0, 2 in there. And so that helps keep track of how the trees work. That helps keep track of all of the data that you need while keeping things nice and fast and efficient, and having really quick lookup, really quick editing. And if new things pop up in between other stuff, or the grid grows in some way, you just keep adding in more elements with more keys. And that doesn't matter. It doesn't slow down other things, and you don't have to like spend a whole bunch of time like shift every element of your array over 1 because you added something on the left. So that's the huge big tip here. We can use a dictionary, and then we can just have the key be a tuple of the x and y coordinate, and then have the value be the height of the tree in this case, or whatever other value you're reading.
Yeah, I think conceptually, just like for your brain, it's also like a lot easier to understand when you can be like, yeah, we're talking about X and Y, or we're talking about rows and columns, and you can just lay it out in that order, because otherwise you'll be sitting there thinking about, was the rows the inner layer of the list, or was they the outer layer? And this way you can just deal in terms that you're used to using, like X and Y, which is really helpful. But yeah, I'll add on about, default dictionaries. We didn't use one for this problem because it didn't need to be like an infinite spanning space. But as Jack said, you might have a place where there wasn't a tree, for instance, or some other two-dimensional problem in the future that's ever spanning, or just has holes in the data. And for these kinds of things, you might want to use something called a default dictionary, which you can get using this code here. And we could have said that trees is equal to default dict, and in this example, they're all integers. So we could have said that its default value is 0, but potentially you could have it be a list. We'll give you an empty list, for instance, if you want to have a dictionary of lists. But the great thing about this is, let's talk about the list example, is if we were to add, for instance, maybe we're adding things to a map of like maybe trees are growing instead, we could just say there is a, hey, go to coordinate 5, 7 and add 1 to the height of the tree, for instance, or something like that. And if the tree had previously not existed and we needed to make it be 1, it could just look up that value and be like, oh, the default thing here is an integer. If we say int, then it would say, okay, the default value is integer. If it doesn't exist yet, it's 0, and I'll add 1 to 0. So it means you can handle your maps with a lot more ease if something doesn't exist yet, maybe because it's on a growing, expansive map that doesn't have any boundaries. With this example, we know that it only goes in this exact size and it's not growing. So it's nice to start with our regular dictionary. But if you encounter something in the coming weeks, that might be the piece of code that you're looking for, and you can look more into that later. And I'll drop some stuff in about dictionaries from our previous episodes of In the Code Garden in case you want to have a look. I'll also drop some stuff about lists and tuples.
Yeah. While Renee does that, I'll wrap up by just quickly talking through the rest of this problem. We won't code it because honestly, we're 15 minutes over time. But basically, once we've constructed the dictionary, which we do at the end of, like, by the end of line 12, by the time we've got to line 13, our dictionary of trees is built. Then the rest of it is just looping through various chunks of this. So to check if a tree is visible, if it's along the edge, then you return true. So that's checking if either it's x or y are 0, or if it's x or y are at the max value. Or as we can see, max minus 1, because of how I calculated max x and max y before, which was just getting the length, and it's all 0 indexed. So that was a really easy spot for an off by 1 error. But we'll just breeze quickly past that. And then we check, and then I basically have the same code 4 times. There are neater ways to do this, but it's fine. It's just, it was easiest just to copy paste and slightly tweak it. But we check all of the trees to the left and check if any of them break the visibility. Otherwise, if it's still visible to the left, we return that it's true because the tree is visible from at least one direction. Then similarly, we do the same for the north and from the right, and then from the top, and then from the bottom. And so then we just have a little function that loops through all the trees and counts up if they're visible and adds a count if they are.
Yeah, interestingly, I did this the other way. I went through and checked if they were blocked in all directions or in any direction. And then, that's kind of the approach I took. So I did slightly different stuff. If that's kind of the direction you've gone with yours and you're still trying to finish it up, you can check out my code. The links to mine and Jack's repos are both on the link that Sarah dropped in the chat earlier, which I'll get at the end to drop at the end of the show.
Yep. And so, then we get the number of trees that are visible. And then part 2 is pretty similar. It's checking how many squares are visible from any given tree. And so that is like, so instead of seeing, can it get to the edge, you're seeing how many steps can it take before it is blocked. And so again, you just loop through going outwards from the tree. And then it wants you to multiply how far you can see in each direction together to get like a score for each tree, and then you find the tree with the best score. I found this problem not the most interesting one, but it does have quite a lot of code, and it does have the dictionaries. So I think it's easing you into the 2D, like the 2D grids that are so common in advent of code. But I found that I just kind of brute force this one a bit. I didn't implement any like fancy technique to, you can generate a slice like this, and then you're going to say, do this magic function, and it all happens. It's all a bit brute forcey, I found, for this one.
I think just doing it 4 times, it's just easier. And you could conceptualize something fancier to do it. But I think sometimes it's just like, no, it's just 7 lines of code, something that we're going to do 4 times, just for the simplicity of the problem.
Yep. The only tip I have is if you do have a problem like this, it really helps to add this comment that I have here where I say like can be seen from the bottom, or put them in 4 different functions where I have like down visibility and left visibility and so on. That just makes sure that when you come back to it, if you take a breather or if you've just moved on for a bit and come back, you make sure that you're editing the right section and that you're changing, what key you're looking at, like what coordinates you're looking at in the correct way. That's my other big tip.
Yeah, I had
comments.
Yeah, I had all my variables named that way. So I had like east blocked, west blocked, north blocked. So you could incorporate that way as well.
Absolutely, yeah.
Yeah, cool. Okay. So, you'll have that code. It'll be in the repository if you want to check it out and see how it goes. But yeah, I guess we have the things, we could run the data, I guess. And then pop it in the thing. And then we can wrap up for today's session.
Yeah.
We get this number. That might be part 2.
That's part 2. 18. Yeah, that one's part 1.
Yeah. We can pop that in. And then we've got our part 2. We'll pop that in too because it's just there.
Yep.
So let's pop that in too.
My other tip for this one is read the problem. I spent way too much time on part 2 because I had off by 1 errors. Because I didn't read the problem and thought that when a taller tree blocked the view, you didn't count that tree. But you do, and I would have known that if I read the problem more carefully, and I would have saved about 10 minutes on working that out. Because I was just getting random results, basically.
My problem in this one came from the copying and pasting and then getting distracted and not realizing I hadn't updated one of the variables from the copying and pasting. So I was testing one thing half correctly and not fully correctly. And then I was just like, how am I ever going to find this in my output? I did have something to show. No, it was actually for the last one, but making things that can print out how you're going through your data.
Yes.
Is super useful. Where is my printing stuff?
Look back and show that. That's definitely worth showing.
Let's go back to day 7. Because I was like, wanted to check if I was processing the data correctly. So I made I put it a function.
You might want to just copy in all of your code or copy in your file.
I'll just bring this one over here for now.
Yeah,
I'll grab my code, view all. So yeah, this is my code for going through my whole tree and then saying if something's a directory, because I've set mine up as directories and files objects. If something's a directory, then we want to go through and print everything out. But so I could get that tree factor, like making it look like it's inside of each other. I went and I gave it an indent. The default. Oh my God, there's a cat going crazy in here. There were 2 cats in here, and I only realized there was 1 cat when I closed him in, and the crazy one is still in here. So yeah, but I added an indent to here. The default one was for the root level, which we didn't want indented at all. But as we go down, I did want it to get more indented. So every time we go in, I add some more space to the indent. And then either we print out, the name of the directory with the indent on it, and then we do it for all of the children with a deeper indent. Or once again, if we get to the files, we just print that file with the indent at the start. So that's really useful. And I'll run that so you can kind of see what I'm talking about when I find it. Here we go. This is my whole problem code. Maybe I don't have the example handy here, but you can see this way. You can see, okay, we've got the root and we've got a bunch of directories and stuff. And that way I did this for the example to check that I was actually processing it correctly. So it can just be really great to visualize things as you're going through it, which I also did for day 8. At some point, somewhere there's a loop here that goes through everything, I believe. Let's just run it and find out. Whoa, that's too much code, too many lines. Oh no. So I'd like to include a debug statement. Anyway, so
visualization is good.
Visualization is good. I just wanted to print out all the trees and kind of print out the ones that were blocked and which were visible, so I could see, like in the shape of the grid, these ones are the ones that you've identified as invisible or visible. So yeah, things are happening here. I don't know where my code's gone, so that's fine. Anyway, that is, with that, we'll say visualization is really great. And for that one, you just went, because we did have those X and Y coordinates, I could just say for X in, the range to the maximum X and for Y in the range to the maximum Y, print out what is in that spot if it, unless it's blocked potentially or whatever you want to do. But yeah, actually looking at what it looks like is really great for comparing it to the example, just to make sure your code even just processes the data correctly, which is really useful. So yeah, as we said before, you can join us on the leaderboard, which Sarah has included at the top. It's also on this repo. So come and join us on our leaderboard, and also come and join us for our next episode. We have moved it slightly to a different day. So this one here, we're on the American Thursday and the Australian Friday. So come and join us on the US Tuesday or the Wednesday for Australia and APAC region. Same time. Or if you also want to join us for some microbit fun, I'll be joined by Helen Cardios-Menos, former school teacher. We're going to do some fun stuff with MakeCode and microbits for the holidays. That will be great for any parent, kid, teacher, or person who likes shiny electronics with lights. So that's coming up next week. You can sign up for either of these on my website, which I'll just grab here for in the Code Garden. And you can, we will hopefully see you then. Thank you very much for joining us for episode 2, Jack. And we'll keep coding in Advent of Code and tell you more about problems. Where are we up to? 9 through however many we get to on the next episode. Probably they're getting pretty big, so we might only look at 1 or 2 and give some tips for the other ones that we thought would be useful.
Yep. Great.
Awesome.
Well, thanks. It was fun to be on. Thanks everyone for joining, and we'll see you next time.
Fantastic. See you all then. Bye.